Good afternoon for everyone. So this is Makluf speaking. Well, thank you very much for joining this first seminar at SystemX concerning the 2022. By the way, I wish you, as for all of the persons, I didn't see them yet after the 1st of January. So I wish you all of you a healthy year and a happy new year 2022. Today, as usual, we are welcoming an eminent researcher who is George Iosifidis. So George, just if you allow me for a short introduction before your talk. So George Iosifidis has received his diploma degree in electronics and telecommunications engineering from the Greek Air Force Academy in 2000. And he also has his PhD degree from the University of Thessaly in Greece. He was a postdoctoral researcher with CERT and then with Yale University in US between 2012 until 2016. And then he was an assistant professor with Trinity College in Dublin between 2016 and 2020. After this, he joined the Delft University Technology as an assistant professor. Please, George, if I am wrong, correct me. And recently, if I understand also correctly, he has also some collaborations with Amazon concerning different activities, research activities. But if I can summarize his research interests in few words, so George has a lot of interest in terms of research activities on network optimization and economics, and also a focus, recent focus on edge computing, data caching systems, and sharing economy platforms. Today, he will talk about a very timely topic with the title of Network Resource Management for Edge Analytics Services. So thank you, George, for accepting the invitation to this seminar at SystemX, and the floor is yours. Please go ahead.
Hello, everyone. Thanks, Makluf, for the invitation and for the kind introduction. Super happy to be giving this seminar, the first seminar of 2022, if I understand correctly, for SystemX. Welcome, everyone, in the talk. Thanks for taking the time to attend. Yes, as Makluf said, I'm currently splitting my time between TU Delft and Amazon, where I'm visiting academic. And this work I'm going to present is the work I do in the university. And I tried here to summarize in few high-level slides. So I hopefully I will not tire you, but I'm always happy to talk about the details if you want afterwards or during the Q&A after the slides. So the topic is about networks, how we control networks when we want to support certain types of new services. I use the term edge analytic services. Another term could be intelligent services or mobile analytic services. Services where we don't just have to transfer data from one point to the other, but we need to maximize the quality criterion, such as the accuracy of some inference, processing the data, and so on and so forth. So let me just start. Usually in this kind of talks, or when we go to conferences, we say that operators face new challenges. They have the growing data traffic to support, and this is a challenge. And this is true. And this is the motivation we used for many years, let's say the 10 previous years when I was a PhD student. This was the opening slide for many papers I wrote. But really today, this is the case that not only we have more data traffic in networks to support, but we have new services like mobile augmented reality, video analytics, right? And new clients. It's not only us, the humans, that are cellular networks and need to serve, need to connect, but also the autonomous vehicles, the drones, robots, or various Industry 4 systems. All these are nodes and nodes at today's or tomorrow's mobile networks. Okay. So this indeed, it's not just a manner of speaking, it requires a shift in the way we design and manage communication systems. Okay, and to put things in perspective, the first, let's say, generations of networks, we were trying to increase their point-to-point data transfer capacity. Okay, we wanted to transfer as much data as possible from one point to the other. And this became more challenging when people start using more the internet and more exchanging more content. So then we focused in particular in content delivery capacity of the networks. Many years later, and quite recently actually, we understood that we need to process the data as we transfer them often, or deploy multi-access edge computing services where we want to process and provide services close to the end user. But our view in the group, and I believe many of us, many of you share this idea, this opinion, is that this is not enough today, because today, in particular, we need to focus on the analytics or the services, on the services that the networks provide, and optimize exactly the quality of those services. So to put it simply, we are not interested in our networks just to transfer many data from one point to the other, not even to compute as many data or process as many data en route as we transfer them. We are interested to process them in a way that maximizes the video service that we offer to a user. Imagine a drone or an autonomous vehicle that runs around and we need to process through the network the video feed of that car in order to help it navigate the streets. Okay, it doesn't matter if you transfer a lot of data from that video stream. It doesn't matter if you have high computing capacity for this stream. It matters if you can return high granularity and confident inferences, object detections, for instance, in the images. Okay, so I think you get the idea that we are after the actual performance of the service. And we claim that the service has to be or should be optimized and controlled by the network. Okay. So before going to the details, let me perhaps give you an analogy to make my point more clear. In the same way we have protocols, we developed protocols for controlling the video quality when you watch YouTube, for instance, on your mobile phone. And then it is now the network that decides together with the servers what should be the quality of your video stream. In the same way, in a similar fashion, we need the network to configure the various parameters of the services of these intelligent services. Okay. So edge analytics, we need to make decisions such as from where to collect data, how much, how often, if you have multiple drones, if you have multiple cars or sensors, how to initialize the data collection, okay? How to transfer this data, to which destinations. You might have many servers that are capable of processing this data, which routes to use in order to reach each of these servers, and how many network resources, how much network capacity to allocate to these flows, and where to process the data. Not only how much capacity, CPU capacity to allocate, but also, and perhaps more importantly here, what type of libraries to use. Let's say you have a server and it has 3 neural network libraries. You need to invoke one of them in order to process your video stream. Which one should be that, right? This, we argue, should be a decision that you make, that is made by the network. So we have new decisions from the network perspective. Okay, we have new metrics. As I explained, we are not only interested in the throughput or in delay. We want to have accurate inferences, many successful AI tasks. There are concepts such as the utility of information. Okay, these are the metrics that modern future mobile networks need to optimize for. And of course, there are also several trade-offs, new trade-offs. For instance, we have nodes that are relying on limited energy, and then they have to do both computations and data transfer. Hence, their lifetime, the operation horizon is limited, and we need to balance the energy consumption with accuracy, or we need to balance the volume of the tasks that the network or a node of the network can execute versus the cost of executing this task, the resource consumption. I don't know why the pen draws both these thick lines and these thin lines anyway. And among all these trade-offs, one that I think personally is quite exciting is the fact that energy is the resource that affects all these operations. It's essentially the common currency that you have to spend in order to do computations, in order to do communication, in order to collect the data. Okay, and not only it is limited, we cannot charge a mobile phone with as much energy as we want, even if we had it, right? So there is limiting capacity in the network that in terms of energy storage, it is expensive. Okay, and also, as you all know, nowadays there is also the importance of the impact on the climate or on the environment, right? So we cannot spend as much energy as we want. Already, mobile networks are famous for consuming a lot of energy and creating a lot of CO2 emissions. If we transition to the scenario that we offer these intelligence services that have AI and computing, etc., over the network and make them as a utility in the same way that we can watch now video on YouTube in mobile phones. If in the same way we can access this type of AI services, then you can imagine what the energy consumption would be, right? So energy is both critical, it is limited, expensive, and it is critical for the environment. Okay. So we have new decisions, new metrics, new trade-offs, the impact of energy, and we have the opportunity, on the other hand, some good news, that we can manage today networks much better and in a more refined way than we did in previous generations of mobile networks. Of course, we all know we have software-defined networks, we have NFA solutions, and all this, what they do is they allow us to merge computing and communication decisions and make them in real time, in the same time scale, which is almost real time in many cases. Okay. So this is at a high level how we think about mobile networks, and I wanted to share our perspective, our view on this with you. And more specifically, motivated by this background, what we have tried to do the last couple of years is we focused on the radio access network, which, as many say, is now the forefront of network research when it comes to mobile networks. We have spent a lot of time optimizing the core networks. Now there is a lot of innovation at the edge of the network. So Open RAN, for instance, which is the next generation of radio access networks, is getting a lot of traction. There are many universities, but also many companies, many consortia that are working exactly on this. And of course, when we talk about Open RAN, the main thing are the virtualized base stations. Okay, so the base stations we have in mobile networks today, previous generations were rigid hardware machines that could do few things very well. We couldn't change their configuration very fast. They were good in doing what we expect them to do. Virtualized base stations are essentially software functions running potentially in different machines, in commodity servers, and they're very flexible, they're very agile because we can reconfigure them very fast. But there are some drawbacks, of course, right? So first of all, this plenitude, this abundance of configuration options, it is difficult to understand which of the configurations is better to select. And also, they might lead to unpredictable resource consumption. For instance, when you have, instead of an FPGA, you have a sequence of functions, it is more likely, it is more easy to have an unexpected exception, an event that your processing terminates before you deliver before you decode the signal, and then you get zero throughput. Okay, so in this context, we worked with virtualized base stations and we tried to solve these two problems. And I have to say, this is a collaboration, you can find the details here. This is a collaboration with NEC in NEC Europe, which is based in Germany, with Andres Garcia Saavedra, Xavi Costa Perez, and Jose, who is now a senior researcher in Huawei in Dublin. And he was a postdoc in my group at that point. So what we studied was how to select the transmission power, the coding scheme, and the airtime for each base station in order to maximize the served traffic you have in a network and also control the power consumption of this base station. And then another problem, which is equally important, how to select the transmission power, the MCS, and the airtime in order to maximize the throughput while not exceeding a certain hard power consumption threshold. Okay, I will elaborate on these two problems in the sequel, but what is common on these two problems is the fact that in order to understand them, we need to answer the following, let's say, sub-questions. What is the performance and the energy consumption profile of the virtualized base stations today, and how can we optimize their operation? Okay, using an adaptive and platform oblivious approach. The energy and performance are new. One would say, okay, George, we have been working on this for decades. We know how a base station works. It turns out that these software-based base stations operate substantially differently from previous base stations. Hence, we need to investigate both the performance and the energy consumption. And then along with that comes the fact that it is not easy to configure them. So we need to learn how to configure them. And for those who are not trusting my big statements that we don't know how to configure them and that it's difficult to configure them, so what we did, of course, we investigated this in advance before going ahead and proposing solutions. We launched several experiments using not very complicated testbeds, just some USRPs and the very nice SRS-LT platform, which is a spin-off from Trinity College. And the power meter, and we measured how much is the energy that a software-based station consumes. Okay, so I will not go into the details here of the setup, but I can, as I said, I can explain later. So we measured different things, and I will highlight the findings at again at high level. So one important thing is that in previous generations, so if you Google, if you search about green networks and green mobile networks, you will find a lot about how to control the transmission power in order to have an efficient a green operation of a network. Okay, because at that point, for this equipment, for big hardware-based stations, the main power consumption element is the transmission and reception. It turns out for small base stations, like those we will have in small cells, and software-based stations, it is equally even more important the computation cost of the computation, the energy spent by the computations. Okay, so your base station, roughly speaking, can be separated in the baseband processing unit and the radio unit. Okay, and here is where the signal processing happens, and here is where the transmission happens. And we see here that the power that we spend when we are idle, or when we transmit to downlink, or when we transmit to uplink, it is more actually induces more cost in computations than cost in transmissions. For this setup, where the setup, you can imagine this as a small base station. Also, we see that the energy that we consume depends on the configuration here, the bandwidth that we use for the channels, and the hardware. Here we use a small form factor PC, another one, a big, which is slightly larger. This was an Intel NUC, and two servers. And we see each time we have a different profile in terms of how much energy we consume. Okay. So what is the takeaway message here? The message is forget about focusing only in the transmission. The computations are equally, if not more, important. Okay, and the second is that the platform that hosts the base station affects its energy cost profile. Okay. Also, because now we have all the radio operations happen through software functions, we see some interesting things. For instance, we see that we can characterize the decoding time, you know, how much time it takes to decode the signal as a function of the SNR. Of course, the better the SNR you have, the highest SNR you have, so your signal is cleaner, you need less iterations to decode it, and which is intuitive. Okay, so it's not fundamentally new, but what is important to remember here is that there are this step increases, and hence there are several trade-offs that you can assess in advance or optimize. Okay, so for instance, you can measure the SNR, and then you know that if it is 20, then when you use higher MCS, which is good for your throughput, you might increase the decoding time very fast and very suddenly. And then this might break the deadlines that the software chain has, and then you get zero throughput. So you observe that you have a good SNR, then you are happy, you say, yes, I will use a high MCS to maximize, to increase my throughput. But then what happens is that because you have this sudden change here, this steep upwards slope, you will have high delay, and your virtualized base station will not be able to meet the processing deadlines, and the signal will drop. You will lose the data. So this gives us, again, some hint that we need to be to change the way we make this mapping from SNRs to MCS. Okay. And we see also that the decoding time affects the consumed power. So you go from SNR to decoding time, and from decoding time to power. Also, let's see the configuration options and the impact of scheduler. I will focus here first. So here it's quite interesting to see that we have 8 different configurations, which we number 1, 2, 3, up to 8, in terms of MCS, airtime, and MCS and airtime actually, and they give all the same throughput. Okay, so we have different ways to achieve the same throughput with a virtualized base station. And what we see is that there is up to 38% difference in the power that you consume. So if you don't take that into account, and this is also platform dependent, the figure is different if you use a different computing machine. Okay, so what does this tell you? It tells you that there are plenty of configurations. It's easy to go from one to the other in your virtualized base station, but you have to be careful, because otherwise you might be losing even up to 40% energy, wasting 40% energy, while you could have achieved, with a careful selection of the configuration, the same result with much, much less energy. Okay, and one final point, again, what we see here is that we always thought that the downlink and the uplink affect differently. This is known result, the energy consumption of the virtualized base station. Okay, and here we plot for different values of the MCS, the energy consumption induced by a stream in downlink, this line here, by a string in uplink, and the joint consumption. And what we see here in this scenario is that in several cases, one of which is displayed here, the uplink consumes more power, while one would expect, if you had asked me 2 years ago, I would say the downlink, of course, is always much more challenging in terms of power, because the device the base station has to transmit. But here, since the processing and the decoding of the signal is so expensive, the uplink actually turns out to be more energy power consuming. And another thing we see is that, of course, they share a large part of the power. Uplink and downlink, they share a large component of power consumption. So if you add this point here and this point here, you will go somewhere here, but the actual cost that you spend if you do both is less, because there are shared components. Okay, so what are the conclusions from these experiments? If we described the power consumption of a software-defined base station, this is something difficult to do. It is intricate. It depends on several things, such as the traffic, the SNR, the coding scheme, how much, what is the constellation, how we modulate the signal, let's say, and how much, what is the duty cycle of the base station, how much time in each iteration we actually transmit or receive. So the first message is that it is difficult to describe it. Hence, all the previous models that had some nice functions telling us this is the MCS that you need to do to select in order to achieve that performance do not hold. At least do not hold for all scenarios. Also, the second finding is that there are many configurations, and some of them present non-linear or even non-monotonic relations with power and throughput. As I explained, you might see that you have good SNR, hence in a typical base station, you would increase the MCS to increase throughput. But if you do that with the SRS, what we saw is that there are some unexpected fluctuations in the decoding delay, and then you'll miss the deadline between the functions in the service chain that implements the base station, and hence the throughput goes to 0. So although you had better SNR, you achieved 0 throughput just because you follow the standard convention that you have to increase. You can increase the MCS. Okay, the power consumption is very high for the BPU platform, and depends on for the BPU, the signal processing, it depends on the platform. It depends also on the scheduler, how you go from SNRs to MCS, and so on and so forth. And because of all this, it's not realistic to say I will have a function that describes the operation of the base station, but instead what we propose to do is to use learning techniques where, as the base station operates, we observe how it works, and we try to learn its function, the operation function of the base station for this specific demand, for this specific hardware machine, and then find at the same time what is the best configuration. Okay. So in other words, we advocate here that for all these reasons, the problem of optimizing the operation of virtualized base stations and virtualized radio access networks is not an optimization problem, but it is a learning problem. Okay, so let me then go into some details about how we model this. Again, I will try to keep it at high level, but some notation is necessary. We define the context. So our goal is, again, at high level, our goal is to optimize, to find the optimal operation of the system, and we will define what the operation means and what optimal means. So first things first, the context for downlink is a vector that we define, and it is it consists of the mean and the variance of the downlink channel quality indicators across all users in the previous period. So we are going to make decisions at periodic decisions at every few seconds following the open run architecture. In each round, what we know is what happened before in the previous round. And we define this with the context vector for the downlink and the uplink. What does this context vector include? It includes the mean and the variance of the channels across all users. So if we have 5 users or 10 users or 20 users, we summarize their channel conditions with the variance and the mean value. And also we have the amount of data that are in the buffers that we need to transmit to those users. Okay, the load. And similarly, we define the status for the context for the uplink. Now, after having defined the context, the next thing is to define the actions. The actions for the downlink and similarly for the uplink is how much power we transmit. So we have the transmission power control policy, which we decide for the next time window. Okay. Then we have the highest MCS that we allow our scheduler to take. Okay. And the maximum VBS transmission airtime. So it is important to clarify here that since we follow the open run policy, here this can be perceived perhaps better as meta policies. So we don't design the scheduler per se, how you go from the SNR to the MCS, but we decide the highest threshold for the maximum MCS. Same for the transmission power. You can use at the real time whatever scheduler you want, but we set the maximum transmission power limit. And the same holds for the airtime. Okay. Similarly for the uplink, we cannot affect the transmission of the devices, but we decide the encoding and the airtimes. The reward is nothing else than a normalized function of the throughput. So we want to maximize the logarithm of 1 plus the rate that we achieve, and the same for the uplink. And we take the logarithm to achieve some fairness between these two, and we divide them with the actual load. Okay, so it's a typical weighted utility function. You can have here, you could have used any other concave function. Okay. So the first problem, returning to the two cases, the first problem we want to solve is how to balance performance and cost. We want to maximize the throughput, and also while not going very bad in the power consumption. So essentially, we want to maximize this function. What is this function? It's the one that we saw here, okay? The function of the throughput, minus a weight parameter delta, a function B that takes as input the consumed power. And this can be, for instance, it can be a linear function, okay? Or it can be a function that captures how much the operators pay for spending this much power. And delta is a weighting factor that allows us to combine in any way we want these two criteria, okay? So we have the context, which is what are the channels, what are the demands, and we have the decisions, which is the MCS, the airtime, the transmission power, how the user should transmit in the uplink. We have the performance metric, and then what we do is we try to maximize, to minimize the regret. What is the regret? Because you have formulated this as a learning problem, we follow the standard convention or the standard approach of learning problems, which is you try to make dynamic decisions over the periods, and you assess their efficacy, how good they are, based on whether they can reach one policy that you could have designed if you knew all the future. Right. So if starting in the morning that you want to configure your base station, you know what will happen all day, what are the contexts, what are the user demands, what are the channel conditions, then you would be able to summarize all these, solve an optimization problem, in particular this problem here. Okay. You sum from the morning time to the last slot until night, and you find the maximum, the single best configuration that gives you the maximum performance for the entire day. Okay, now of course you don't know in the morning all this day how it will evolve, so you have to make successive decisions about XT. Here maybe it's better to show. So you have to select configurations, and you want this gap here to be as small as possible. To be more specific, you want this average loss to go to 0. If this happens, you say that I managed with this algorithm to learn the optimal configuration of the system, and you are happy because you achieved asymptotically zero regret. Okay. So here, one key thing to remember is that the outcomes of the different configurations are correlated. Okay, so let me take a step back here, because we like learning and machine learning optimization and learning theory, but we also want to be pragmatists and see what is the actual problem. So I think I motivated that you can forget about traditional optimization techniques because you don't know the functions essentially of the system you want to optimize. This is in a nutshell what I was saying with so many words. Okay, but then we should not go to the other extreme, saying that you don't know anything about the system behavior, because we know more or less that if you increase the MCS, unless you are at the edge, at the end of the spectrum of the values that you can support, usually, normally, many times, very often, when you increase the MCS, you get a better performance, okay, for instance. So we know that there is some structure there, some hidden function that describes the system operation, but we don't know what this function is. Hence, when we do learning, we need to remember that there are some correlations between the different configurations. So you have the configurations, these are the input to an unknown function, and then you observe the output, okay? Instead of treating this as a black box that does not have any structure, we need to remember that if you go from one configuration to the immediately next one, which differs only in one parameter, then it's quite likely that the outcomes will be similar. And we want to know, without making many assumptions, how similar they are and learn from this. In few words, whenever you try one configuration, you don't only learn or observe what is the performance of this configuration, but you learn perhaps some things for other similar or nearby configurations. Okay, and the next version of the problem we studied is what happens if the objective is to maximize throughput, but not to exceed at the same time hard power constraint. So imagine that you have a virtual base or a base station in a far location that you power over Ethernet, okay, and you don't have a battery in the base station. So in that case, you need to select configurations that spend only as much energy as this power over Ethernet line can feed your machine. Okay, or maybe this is a green operator and they want not to exceed for any reason this hard power threshold. This makes the problem fundamentally different. From an optimization perspective, you don't have now a weighted scalarized objective, throughput times a factor and the consumed power, but you have throughput subject to a hard constraint. Now, hard constraints are not something that scares us usually, but they are scary when you don't know the function, right? So we don't know what is the power consumption of the base station and how the different contexts or how the different configurations affect that. Hence, it is difficult to be selecting configurations without knowing how they can affect the power. Again, the idea here is to find configurations that are good enough if we compare them with a single best configuration over the entire day. We want to adapt to the context, observe what happens in the past, and always select the configuration that it is in the set ST, which is the set of the configurations that are safe, in the sense that they do not induce higher power consumption than Pmax. Okay, some more analytical stuff, and I will go through quite fast now because I think we are spending more time than I was planning. So how will we solve this problem? We do Bayesian online learning. At a nutshell, this is the following. We use Gaussian processes to learn the functions that we don't know as we get more and more data. Okay, so every time we collect a data point, which is an observation, which is the context and the action, then we apply this in the system, we configure the base station, we get some observations about its performance, its power consumption, then we update the statistical properties of these Gaussian processes, and then we estimate the mean and the variance of the functions that we don't know. And based on these mean and variance functions, what we do is that we use the acquisition function and select the configuration that maximizes the maximum expected value plus the variance. Okay, so essentially we apply a bandit algorithm where we pull different arms, but the information that we use comes from the Gaussian processes, the information about what each arm will give us. Okay, so this, I forgot to add the reference here. This comes from a famous paper by Krause et al. That was published in ICML conference in 2010. And I think last year it got the Test of the Time award from that conference. And here is a visualization of what we do actually. So the dotted lines is the unknown objective function. Okay. The shaded blue line is the uncertainty we have about the function at any given point. For instance, here we selected this configuration, hence we are able to know exactly what is the function value at that point. In nearby areas, I can leave this here. In nearby areas, we have less uncertainty because they are close to our observations, so we learn more about these areas as well. But as we go further and further from the observation point, the uncertainty increases exactly because this observation doesn't tell us much for this area. Okay, and then what we do is we use the acquisition function that maximizes a certain weighted criterion where we go to select actions where we expect the value to be high, but also there is some uncertainty there. So we want to keep exploiting what we know about the function, but also exploring. And as we collect more and more observations, then we learn more and better with more accuracy what is the function that actually is there. In our case, what is the function that describes how the configurations affect the performance, and hence we are able to make better decisions. Okay. So Bayesian learning actually is used in all kinds of things. And let me just summarize that, state that, for instance, in the way that you design experiments for vaccines, or in the way that you make decisions where to drill next when you try to find oil or natural gas or whatever you are looking in an area that you don't know what is underneath. But it has also some technical difficulties. In particular, one challenge is when you use it in runtime, there are some computational, so there are some technical challenges that how to invert some matrices. Okay, and here is the algorithm that we already discussed, and the result is that there is some probabilistic bound for the regret, for the optimality gap. So if you divide this with t, you will see that indeed it goes to 0. The safe algorithm, which is the one that we use to solve the problem with the constraints, is not very different. But here we need to use one Gaussian process for the objective and one Gaussian process for the constraints. And then through them, we do this exploration by taking the mean value of what we expect will be the outcome of a certain configuration and the mean value of what we expect to be the power consumption of a certain configuration, and we make additional corresponding decisions using the acquisition function. Okay, so what we did after designing the algorithms, we used the testbed to evaluate their performance, and we see here some things that they were rather expected. First of all, for a typical setup, these are the number of different configurations you have. Okay, so they are quite a lot. It is difficult to go one by one and find which is the best to use. Hence, you need this learning technique. Okay, then we see that parameter beta, which is the parameter that prioritizes either the performance or the throughput or the power consumption, does affect a lot the result. So if beta is 25, then you get a higher power because there was a minus b times the power. If it is smaller, then the priority is on power and you get less power. We see that there is some learning in the beginning, but then it stabilizes more or less the performance. There are variations because there are noise observations due to meters and everything. And similarly, the results for the throughput. In the case of the safe version of the algorithm, the version where the constraints, we have hard constraints for the power, we see that we are more conservative in the beginning. For instance, here, we explore slowly the configurations. We try to maximize throughput. Here is the respective area, it increases. And we do that without exceeding the threshold, which is the dotted lines here, the dotted line here. Okay. So we see a different approach. It's more slow in the beginning because it explores the different configurations, making sure that we don't exceed the power threshold. And we also evaluated the performance using actual data, verifying that it does adapt to the variations of the traffic. And concluding, what I explained this many times, but let me summarize very quickly. We presented in these works, we included a detailed experimental study of the energy behavior of virtualized base stations, but also of their throughput that they can achieve. We found that there is a complex relationship between performance, power, cost, and the possible configurations. We argue that this is difficult to model and solve with traditional optimization techniques, but you need to do learning so as to adapt on what you see when the system operates. We proposed a solution for that. This solution has some theoretical guarantees, and in practice, it has high data efficiency. Especially in this line of work with the online learning, it's often the case that you get nice or maybe nasty theoretical guarantees, but then in practice you see the empirical performance to be different. And actually, even in machine learning optimization, as many of you know, it is more and more common to focus on the empirical performance. Empirical performance needs a proper evaluation, and we did that with the real data and implementing this in the testbed. And actually all the code and all the data you can use freely. They are available in Jose's site. Now, if I have 3 more minutes, I would like also to explain that what we did now, what I presented, was how you learn how to configure virtualized base stations that are the state of the art now in mobile networks. And the criterion was throughput, right? But if you remember in the beginning, I talked about edge analytics and how you need to maximize things such as the accuracy of inferences. One very good example that I like to use often is the application of Microsoft Sync AI, which is an app. You can actually download it in your iPhones or Android phones that you use, and then you take a picture or you point it to a certain direction, and then it processes the feed of the camera and tells you what you are watching. This is very useful for people that have visual impairments, difficulties to see, understand things, right? And this is an example of a service that we want to have accurate inferences. We need to be able to know exactly what the person is looking. The person needs actually to know what is looking at, and it needs to be fast, because if you point the device to a certain direction and then the delay is very large, and in the meantime you have changed position, then you will get an information that it is irrelevant and misleading. Okay, so your system needs to optimize jointly all these decisions, and our approach is that the network is the one that needs to do this optimization. And we have studied 2 versions of this. When you have this kind of edge analytic services over Wi-Fi, and we studied how you should define the frame rate and the frame quality that the user device captures, of the images that the user device captures, how you should define the airtime of the Wi-Fi to the different users, and then how you should also select the neural network that processes this at the edge server. All these parameters affect both criteria, the accuracy of the inferences and the delay. And you can find in this paper the details, also available data sets and codes for this implementation. And another twist of that is when you have a virtualized base station. So if you go back to the first idea of configuring the virtual base station for throughput, here we change the criterion of throughput to the accuracy of these services. So you have a cellular network and you have video streams coming from user devices or autonomous vehicles or drones. You select the frame rate, the frame resolution, the encoding, how much you compress, all these things together with the configuration of the base station and together with the configuration of the edge server that runs the service. And since, again, doing experiments, we find that all these parameters affect in a non-trivial fashion the performance criteria, and in a way that depends on the data, in a way that depends on the equipment. Hence, it is difficult, again, to create in advance optimization functions, models, and optimize them. So you have to do learning on the fly. And in the interest of time, I will skip the details, but I think we can discuss them offline or now if you want. So thank you very much for your attention and your patience.
Many thanks, George, for the interesting presentation. Now I think it's time to try to get some questions, but maybe before asking the audience, I think that we have 2 questions from in the chat, if you can take a look on them. What should one do if there is a concept drift later on? I think that's about the if I got the correct sense of the question, maybe it's about the reconfigurability of the algorithms if they are running online. Are they let's say some algorithms we can actually reconfigure on demand when we want according to the given situation? I think that's about the optimization part around slide 12, if I understand the question. I don't know if Jamal Zigrash is actually here. Yeah, he left actually.
Yeah, so the idea, I'm not sure I understand the question, but let me rephrase perhaps how the algorithm works. The idea is that you don't make any hard assumptions before the system starts running, right?
Yeah.
So you select a configuration, then you observe some throughput, then you observe some power consumption, then you update the probability distribution of what you think the system does. Right. And then based on this updated probability distribution, you select the best configuration, one that balances the, explore, exploit trade-off. So you try to learn at the same time what is how the system really works, but also exploit what you have learned so far in order to select a good configuration. Hence, you don't have to again, if you have a different equipment or if you have a different context, more demand, less demand, better channels, worse channels from the users, yes, these decisions adapt.
Okay. The next question is on the chat, of course. Assume that the data does not change, periodically refit, periodically update, weight data, learn the change, detect and choose model, data preparation. But I think I don't get the question. I don't know if Lawrence is still among us. No. Okay, maybe as the question is not clear, maybe we take some questions from the audience actually, and if there are some questions, please don't hesitate to unmute yourself and take the floor. Any questions from the audience? Maybe one question, George, about the, I think it's around slide 12. You said that yeah, I think, yeah, in this part, you talked that you think that the optimization actually concerning these problems, I mean, these problems are not more on optimization, but that's about learning, right? Mm-hmm. And can you give us maybe more explanations on this point, and maybe clarify where are the differences actually between the learning and the optimization?
Yeah, that's a very good question, and actually, I'm not sure if there is a standard definition, but from a network management point of view, so how I see this is as follows. So if you go back to the network utility maximization framework, which is the concept we use to describe how we optimize protocols, et cetera, yeah, one simple case is that you have, let's say, a routing problem. Okay, let's make it more simple. You have a routing problem, and then you have some routes to select, and then there are data packets that arrive over time. So if the process that generates the packets is a nice process, a nice stationary process, maybe they are generated in an IID fashion, and you know the mean value of this process, then you can write down a nice static optimization problem, yeah, and solve it using the mean value. And then this will give you a routing policy that tells you, okay, half of the time you send that way the packets, half of the time, right? So this is the simplest case. And actually, many of the things we do in the networks, even today, are based on this approach. The next step, where we use not static optimization, but stochastic optimization, is when these nice stochastic properties are there, but you don't know the mean value, okay, to put it simply. So in that case, we have policies such as the max weight policies, the back pressure policies, that essentially use a stochastic gradient update, and they just observe the current backlog in the queues, and they say, okay, since the backlogs are this and the channel conditions are that, then you should send them here and there. Yeah, the packets. Okay. So now the next step with what I understand or what I have in mind when I say learning is that not only you don't have a nice stochastic process that creates the package. So you might have a process that it does not have a nice mean value, or it's not stationary, or it can be even, the package can be even the result of an adversary jamming your system. But also at the same time, even worse, you don't know what is the objective function you want to optimize at that point. For instance, you don't know the routing cost, while in the previous cases, you knew the routing cost, right? So if you don't know the routing cost, because the price will be revealed after you send the data, or because the congestion depends also on other factors that you don't control, then this is not only a dynamic optimization problem where you make dynamic decisions, but you make decisions without knowing the objective function at that point.
Yeah,
so
yeah.
That's how I, at least from my point of view, understand that this is a learning problem and not an optimization problem.
Yeah, but it seems really very close to stochastic optimization. If you go back to just move to slide 13, I think the next slide, maybe the next one, in which you mentioned that there is the probability of a regret, right? So typically, yeah, considering this kind of, I don't know if it's an object or constraint, it will give you, as it is stochastic, it will give you a worst case and the better case in which actually you define the domain in which you try to optimize. So is this something different from the learning? Because when I try to compare them, when hearing you, this is exactly the same thing, right?
Yeah. Yeah, as I said, the difference I say is that you don't know the function when you make the decisions. Yeah. And the function can change in an arbitrary way. Yeah. But again, I'm not sure if there is a universally agreed definition of, because as very correctly, as you say, the differences are sometimes difficult to identify.
Okay, clear. Thank you. Are there any questions from the audience? All right. I don't know if in the chat if there are some questions. All right. Okay. So if there are no more questions, I would to say thank you again, George, for your time, for your interesting presentation. As you not yet send me the slides, please, if you can send them to me, and then I will share them with all of the participants.
Yes, thanks, Makhlouf. Thanks everyone for taking the time to attend. If you have any questions or if any suggestions, even more so if you have any concerns about the work, we are always very happy to receive feedback. And this is something that we keep working on. Yeah.
Okay, thank you so much. And of course, as I said at the beginning of this presentation, we will keep in touch for other topics, actually.
Of course.
Thank you, George.
Nice meeting you all.
Thank you, all of you.